Good day. My name is Marcelo Dilag from ECE109-E01 about to discuss thermocouple. First, what is thermocouple? Thermocouple is composed of two metals joined together to form two junctions, where one is connected to the body whose temperature is to be measured. This is the hot or measuring junction. The other junction is connected to a body of known temperature. This is the cold or reference junction. Therefore, thermocouples measure unknown temperature of the body with reference to the known temperature of the other body. A wide range of different thermocouples are available for different applications, based on metals with high conductivity such as iron, nickel, copper, chromium, aluminum, platinum, rhodium, and their alloys. Sometimes, a particular thermocouple is chosen purely because it works accurately for a particular temperature range, but the conditions under which it operates may also influence the choice. For example, the materials in the thermocouple might need to be non-magnetic, non-corrosive, or resistant to attack by particular chemicals. Here is the part of the thermocouple. Labeled 1 is the protective metal sheet made from stainless steel or an alloy, perhaps nickel and chromium. Label 2 is the first wire made from one metal. Label 3, second wire made from a different metal joined to first wire to make a thermocouple. 4. Insulation made from crushed and compacted mineral oxide. 5. Cement to hold insulation in place. 6. Electrical insulation made from rubber or plastic. How does thermocouple works? Thermocouple follows three principles: Seebeck effect, Peltier effect, and the Thomson effect. Seebeck effect states that an electromotive force is generated at the two junctions when two different metals are joined together. Peltier effect states that an electric force is generated within the circuit due to the different temperatures of the two junctions of the circuit. Thomson effect states that an electromotive force is generated within the circuit due to the temperature gradient along the entire length of conductors. In most of the cases, the EMF suggested by the Thomson effect is very small, and it can be neglected by making proper selection of the metal. The Peltier effect plays a prominent role in the working principle of the thermocouple. What you see here is a representation of what is inside of a thermocouple. In practice, it's wired into a larger circuit with the two outputs feeding into an electronic voltage amplifier. This increases the very small voltage difference between the two parts of the circuit, so it can be measured more accurately. Thermocouples are widely used in science and industry because they're generally very accurate and can operate over a huge range of really hot and cold temperatures. Since they generate electric currents, they are also useful for making automated measurements. Here is the diagram of the thermocouple circuit. It is composed of two dissimilar metals labeled A and B, two junctions labeled P and Q, temperatures T1 and T2. When T1 and T2 are equal, it generates an equal EMF with different polarity, forming a net current of 0. When T1 is not equals to T2, net EMF will not be 0 and there will be current flowing. The device for measuring the current, EMF, is connected within the circuit of the thermocouple. Note, thermocouple cannot be formed if there are no two junctions. Here are the types of thermocouple. Type K, which is inexpensive, accurate, reliable, and has wide range temperature. Type J, smaller temperature range. Type T, extremely low temperature. Type E, stronger signal and higher accuracy. Type N, same as Type K but slightly more expensive with longer lifespan. Type S for high temperature. Type R, higher rhodium percentage than Type S. Type B has the highest temperature limit among the other types. As an ending remark, I will show you a video where thermocouple is used in a demo to read the varying output voltage of an op amp.
Okay, so here's our thermocouple circuit. This is the actual thermocouple, the sensor. And then this is the two leads of the thermocouple. This is attached to virtual ground. And then this is the output voltage. And what we're doing here is using a single supply op amp to amplify the voltage difference between the two leads. We're doing that because the voltage difference between these two is too small to be sensed and to be useful for our project. So as you can see here, it's attached to a power supply of 5 volts, and then this is the output voltage when the multimeter is attached to across the leads of the thermocouple. And as you can see, it's much less than 1 millivolt, and it's changing on the order of about a thousandth of a millivolt. But as you can see, when I hold it and warm it up, it is slowly increasing. But again, it's only about a thousandth of a millivolt. So what I'm going to do is quickly change the multimeter to be sensing the output of the op amp, and you'll see that it is indeed magnified. Okay, so now you can see that the multimeter is attached to the output of the op amp. And then because this is a 1000 ohm resistor and this is a 1 mega ohm resistor, we should expect to see a gain of around 1000. And if you look at the multimeter here, it is indeed about 1000 times larger than it was before, because it's on the order of about a little bit less than a volt right now, and it's varying on the order of millivolts. And if I hold it, you should see it slowly increase. It's not very steady, but it is indeed increasing on the order of about millivolts. I'm going to set this down right now, and I'm going to show you a more dramatic difference by using the soldering iron. So there they are touching. I'll move this out of the way so you can see. But as you can see, it is increasing much faster now. Okay, so I'm not going to bore you with this, but I just wanted to show you that it is indeed increasing about 1000 times as fast as it was before.